Okay, so let me come to example 1.2.2 of lecture 25. Basically, it is lecture video 25 and the corresponding lecture notes where this problem was worked out. Okay, and in my last interaction with you, I told you that I was going to deal with this, but I couldn't do it because I ran out of time. So now let us have a look at this particular problem. So what is this problem? If a vector value function f, of course it is a two-dimensional function, it is given by this expression, it is given by this expression. So then you have to show that your line integral of f, of course, from this symbol itself, you can see that the line integral of f, along the curve C, which is a closed curve, f dot dr, it is going to provide you with the value 2 pi for every positively oriented simple closed curve that encloses the origin. So basically, if I want to find out this integral, in xy plane, over a curve C. So what is the property of the curve C? Like, it has to enclose the origin. That's it. Nothing else. So basically, it is telling you that whether I take a curve, is it positively oriented? Is it clockwise or anti-clockwise? This is clockwise. So I have to take it. What? Anti-clockwise, isn't it? So this will be a positively oriented curve. So whether I take it like C1, I may have something like this. I may have C2. The only thing that, the only property that these curve possess is that it encloses the origin. So whatever curve we take, we are going to end up with the same result. So that is the question. So in fact, while working it out, it involves a lot of concepts, and primary amongst them is nothing but the application of Green's theorem. So that is why I would like to start with your Green's theorem. First. So what it tells you is that if C is a positively oriented, piecewise smooth, simple closed curve, and it bounds a region D. So basically, you should have a simple closed curve. Which is positively oriented. Okay. You know the meaning of simple closed curve. Simple is nothing but a curve. It is not going to cross over itself. And closed, its initial and terminal points are going to be the same. Okay? And it doesn't necessarily have to be smooth all around. You simply need piecewise smoothness of this curve. So you may have this to be something like this. You may have something like this. Okay? Fine, we don't have any problem. Okay, it is piecewise smooth. Fine. And what we do, for the sake of simplicity, we draw it like a smooth curve. Okay, and if it encloses a region D, so then Green's theorem, what it tells you is that P dx plus Q dy. So this is given by del Q del x minus del P del y, your dA. So basically, a line integral is converted into a double integral. That's what happens. And again, it doesn't tell you whether D is a simply connected region or a multiply connected region. Okay. So what I'm going to do, because we have already given the proof for simply connected region, it is pretty straightforward. The way I have got this domain, it is a simply connected domain. So we already know Green's theorem for simply connected domain. So now, firstly, what I'm going to do, I'm going to extend, extension of this Green's theorem. I'm going to do it over multiply connected domain. Okay, and so that means we have a domain which is a hole in A. Fine. So now consider a domain like this. Consider a domain like this, which is a whole. Okay. So obviously, it is bounded by. I mean, what happens if we say that it is bounded by a curve C? Here, of course, it is bounded by curve C, which is nothing but the union of two curves, C1 and C2. Say this is C1, okay? And suppose this curve is C2, this curve is say C2, this curve is say C2. Now the point is that, again, if you want to apply Green's theorem, then what you must have, your curve C must be positively oriented. So what is the meaning of positively oriented? That, I mean, whenever you travel along that curve, the region under consideration, region that it encloses, that region D, right, it must lie on your left. So for this one, it is pretty straightforward. So again, if I want C2 also to be positively oriented, so then what must happen? This one must have this orientation. So then if you are moving across it, so then this region is going to be to your left. Okay, so now I have got C. So I want to prove your Green's theorem, that Green's theorem is valid in this region D. This is nothing but the violet colored region here. Region D, I mean, it is going to be applicable there as well. So for that, what we are going to do, we are going to make something like, say, two crosscuts. Two crosscuts, okay? And then this is going to divide the given region D into two parts. So one is going to be what? One is going to be, I mean, bounded by this curve, say this, then this, and this. So it is going to be something like this. Okay. So let me call it D1, and similarly the other one I'll come back to that later on. So now let me call this part, say this was curve C2. Let me call this part of C2 as C2A, and this part of C1 as C1A. So likewise, for the other part, I'm going to call it as, I mean, C1B and C2B. Okay, so basically the original region D is nothing but union of D1 union D2, where this is D1 and suppose this is D2, right? So then for this double integral D, whatever may be the integrand here, of course, here I'm going to take del Q del X minus del P del Y. Okay, so this integrand, I mean, this is simply going to be union of D1 and D2. Okay, so let me just use this symbol for it. You know what it is. dA, and then this is eventually going to be your D1, D2, dA. Okay, so now let me come to the region D1. If I come to the region D1, so then it is something like this. So this is C1A. Let me call it your C3. This is C2. Let me call it C2A, and let me call it C4. Let me call it C4. Is it okay? Fine. So this is nothing but my region D1. So now again, now you can see that I have converted what? D1 into a simply connected domain, and I know that Green's theorem is valid there. So if I apply and if I call this whole curve, as say C bar, so then this part is going to give me simply C bar, again P dx plus Q dy. I'll come back to this part later on. Okay. and then your this is simply going to be nothing but your again let me for this part let me use something like star. Suppose this is star. So this is simply your C1A star plus your C3 star, okay, plus C2A star, why not write it like this, plus your C4. Fine? Okay. And similarly for now, let us come to this part. Let us come to this part. Again, if I want to dissect this part as this, so then it is going to look like, say, this is your C2B, and this is going to be C1B. This is going to be, am I okay? No. This is I got it wrong. I got it wrong because C1 it is going to move along this direction. So C2 was moving along this direction. Okay. So this is going to be like this. This is going to be like this, and then it is going to be like this. Then all my directions are going to remain intact. Okay. So now you know that. I mean, because this part and this part, they are nothing but the same, but they are in the opposite direction. So that is why I can write this as minus C3 and write this as minus C4. And always remember, whenever you consider line integral with respect to x and y, so then what is going to happen? For this star along any curve, say C3, so this is going to be equal to what? Or if I want to write minus C3, it is going to give me minus of this integration along the curve C3. Okay, is it okay? So then what I am going to get? From here, it is going to give me your, C1A, then C1B, then C2B, and then eventually making use of these facts, I am going to get it C3 this minus C4 this. Okay, so now you can see that this C3 is gone, C4 is gone. Okay, and again if I consider C1A and C1B, C1A and C1B, it is going to give me the whole curve C1. So similarly, C2A and C2B, they are going to give me the whole curve C2, right? So that is why this eventually is from here. This eventually, what I am going to get, eventually this is going to lead me to simply C1 this plus C2 this, and this is nothing but I can again write this as C1 union C2, right? So this is giving me C1 union C2 this. So eventually C1 union C2 is nothing but your C. So this is simply C P dx plus Q dy. So in that way, your green theorem is valid for multiply connected region as well. Okay. So now at the very beginning, when I was talking about the problem 1.2.2, so what I need to prove is that you take any curve around the origin 0, 0, right? It is going to give you, for that particular integral, it is going to give you the value what? 2 pi. It is going to give you the value 2 pi. Okay. So for that, what I am going to do now, if you recall, and again remember, it is talking about any curve which encloses the origin. That curve is positively oriented. Okay, fine. So I have to take that curve I mean in the anti-clockwise direction. So if you recall, my function was of this form, pi plus qj, and where your p was equal to minus y by x squared plus y squared, and q was equal to x by x squared plus y squared. Okay, fine. And let me guarantee you that you are going to find it yourself. You are going to find it yourself. Let me guarantee you that your here, I think your del q del x minus del p del y. Del p del q del x minus del p del y, it gives you 0. It gives you the value 0. You can easily check this here. Okay. So now let me come back to this. Suppose I consider any curve, say C. So maybe I'm going to make it a bit twisted so that it doesn't look like a circle. Okay. So what I'm going to do, I'm going to make it look something like this. Say this is a positively oriented curve C, and obviously it has enclosed the point 0. It has enclosed the point 0, that is nothing but the origin. So here, what I'm going to do, I'm going to introduce a circle of radius, maybe say epsilon, or any radius you can take, which is inside the original curve C. Okay, so basically, I'm going to consider a circle like C1 enclosed within the closed curve C. Okay, and remember, for this curve also C1, I have taken orientation in the positive direction. I mean, not positive direction, sorry. I have taken orientation in the anti-clockwise direction. Okay, so now let us come to this multiply connected region. Okay, which is inside the curve C, but outside the curve, outside the circle C1. Okay, so this is my region D. So we already know that I will be able to apply Green's theorem in the region D, provided it is bounded by a curve C which is positively oriented. Now obviously C, if I want to consider it as a union of, say, let me call it C bar. Obviously if I want to consider it as a union of C and another curve, then I already have positive orientation for C, because I can see that if you move along C, what you are going to see? You are going to see this region towards your left, right? But the other one, here you can see if you move along C1, then this region D is going to be to your right. So, but if we choose this to be, if I choose this to be minus C1 in this direction, so definitely from this union you are going to get a what? Positive orientation of the curve C bar. Okay, so that is why what is going to happen if I apply Green's theorem, here, right? So this is going to give me C bar P dx plus Q dx. So I have already told you, you can easily work it out that this is 0. So from here I am going to get 0. And again here you know that this is nothing but the union of C and minus C1. So eventually this minus C1 I can convert it into minus this. Okay. So this is P dx plus Q dy P dx plus Q dy. So now basically what I have got from here, I have got that this C P dx Q dy, which was my original curve, right? Which I closest the origin 0, so it has become C1 P dx plus Q dy. But the difference between C and C1 is C is any arbitrary curve, and C1 is what? Along the perimeter of a circle, along the circumference of a circle. Okay, fine. So now you can easily work it out. Now, if I take its radius to be epsilon, so then what you are going to have? You are simply going to have what? Your P to be equal to minus epsilon, say sine theta. If I want to convert this into what? I mean, if I want to parameterize it, if I want to parameterize the circle C, right? So then your P is going to be this divided by epsilon squared, and so this is minus sine theta by epsilon, and what? Your Q is going to be similarly cos theta by epsilon. Am I correct? Yes. So then if you want to perform the integration here, so from here you are going to get theta, theta going from 0 to 2 pi, and then I can bring 1 by epsilon out, and then this is going to give me, for P I can simply put minus sine theta, and dx is going to be what? Because your x equal to epsilon cos theta, isn't it? X equal to epsilon cos theta. So dx is going to be minus epsilon sine theta. So it is going to be minus epsilon sine theta d theta. I'm going to take it out. And similarly for this, it is going to be cos theta, right? Since y is your epsilon sine theta, so that is why it is going to give me epsilon cos theta d theta. So here you will see that this is simply going to be sine square theta plus cos square theta, and epsilon is going to come out. That is going to be cancelled by this. So simply it is the integration of d theta between 0 and 2 pi. So eventually it is going to give you pi. Okay. So you may be thinking why I have taken special care of this particular example. It is because later on in your second year, you were in MA 201. You are going to study, complex variables. So over there, you are going to deal with analytic functions. Okay, you are going to deal with analytical function, and you will come across, Cauchy's theorem. It is going to be something like conservative vector field. Okay, and the same example, I think you have to prove that. Something like this, same example, you have to prove that this is equal to 2 pi, and that is going to come in very handy, and you will see that this is exactly the same problem. Okay, so hopefully once you study MA 201 at that time, you are going to remember me. Okay, so thanks a lot for attending.